Okay. Notice I've got shared up there the week we're on. This is our final week with lectures, new material. We'll be covering 4 sections from chapter 10, just the conic sections and some inequalities, and then we'll do 1 section from chapter 11. That's the binomial theorem. And then we're going to test on that. That test will be this weekend. Seems like we just tested, I know, which we did. And as a matter of fact, I've got all those grades upgraded for the partial credit. So your grade in there should be what it will be for that test. And then next week, we just have review and final exam, which is in 2 parts. There's a department-made section, and then there's a section that I made. So those will be the 2 parts you'll take next week. The signature assignment is due this Sunday night, so make sure you get that done. Are there any questions? Okay. So I've got another sheet here that I want to share with you, and this is the Conic summary sheet. It is available to you. It's in Blackboard. It's in the 143 shell, I know for sure. And I'm not sure it's in the 142 shell. I would say probably not. Yeah, it isn't, but it is in the 143 shell. So you can go print this out, and I highly recommend you do so, because it will make the first 3 sections of chapter 10 far easier. And that, to me, is pretty important. I want it to be easier for you rather than harder. And so that's why I put this out there. And you can use this sheet on the exam this weekend and on the final exam. So that's another reason to have it printed out. So you have it available to you and ready to go. So one of the things that I always do when we get to this section is I pull up this sheet and we just talk about the sheet itself. I think that's really important, because then we understand just what it is we're looking at and how to use it. Now, before we get to that, I do want to mention that this is called the conic summary sheet because it summarizes the conic sections. And I like to show a picture to you of why they're called conic sections, and I forgot to load it up. So I'm loading that up now. It's on page 720 in your text, but let me bring it up and I'll share it with you so you can see exactly why we call these conic sections. So let me share that. Should be popping up here soon. Okay, there we go. So this is why they are called conic sections. Notice they took 2 cones and placed them tip to tip. And if you run that salmon-colored plane through it such that it comes out one end of one of the cones, it creates a parabola. If you run the plane through either of the cones horizontally, it creates a circle. If you run it through one of the cones at an angle without coming out the end of the cone, it creates an ellipse. And if you run the plane through both cones vertically, you create a hyperbola. So these are the shapes that we're defining right now: a parabola, a circle, an ellipse, and a hyperbola. Now, we've already talked about parabolas quite a bit. And we've talked about circles a fair bit. So ellipses and hyperbolas are really the new ones. We are going to look at the function for a parabola slightly different than we saw before. And let's see, and so that's an update. Let me go ahead and share in the conic summary sheet with you. And we'll talk about some of these differences. So just looking at the equations themselves, we see some similarities and some differences. Notice we've got circle on the top, and then we have a couple of equations for parabolas, and then we've got a couple of equations for ellipses, and then a couple of equations for hyperbolas. Well, if I look at these, an ellipse and a hyperbola, those equations have denominators, and we're using A and B for those denominators. There is not a denominator for a circle or a parabola, unless you wanted to consider one. So we could consider that there was a denominator here of 1 and here of 1. But I don't know that that will help us much. It just shows that the denominator is the same there, if there were one. Another thing I would like to point out is notice we've got x minus h appearing in each of these. And everywhere we have an x, there is an associated h. And the same thing down here in the hyperbola. It's always x minus h. That will always be the same. So that also suggests that we need to look at the y, and with y, we always see a k. So here's something we need to notice. The center of a circle is the point hk. The vertex of a parabola is hk. The center of an ellipse is hk. The center of a hyperbola is hk. So that's why h and k are so important, and they show up multiple times. H is always the x component of the center or the vertex. K is always the y. And that's why we always see h with x and k with y. We have, with a circle, we've got the radius is r, and we've already talked about that, how the sum of the two squared terms equals r squared for a circle. So that's not new to us. Let me scroll down a little bit. Notice, like I said, we have two equations for a parabola. I'm going to draw a horizontal line here. Well, it's somewhat horizontal. Everything above that line deals with this equation where x is squared. When x is squared, the parabola opens up or down, just like the equations we've seen so far. When y is squared, the parabola opens right or left. Now, we've talked about these equations a few times. When we have one of our variables squared and the other is not, we knew it was a parabola. Generally speaking, we had x squared, so it was opening up or down. We haven't spent a whole lot of time with parabolas that are opening right or left when y is squared, but we will here in section 10.1. We will get to what the focus and the directrix are in a minute. I also want to highlight that the ellipse had two equations, so we need to look at the differences between those two. Notice that with this one, a squared is under x, and down here, a squared is under y. Notice that the top one, where a squared is under x, we get a horizontal major axis. Well, the x-axis is horizontal. Major axis would be the longer axis. Recall that an ellipse is like a circle that has been flattened, or a circle that has been squeezed side and side. So if you've got a vertical major axis, the longer one is up and down. If you have a horizontal major axis, the longer side is left to right. So that's what we're talking about here, and why we have the two equations. All of this information on the right-hand side fits either one of those equations. The longer axis is the major axis. The shorter axis is the minor axis. A is the distance from the center to each vertex. And so from the center out here to the vertex, that would be A. B is the distance from the center to the end of the minor axis, which would be out here. So that would be our B, the distance from the center to the end of the minor axis. The same thing would be down here when it's vertical. Here's our center. That would be the vertex. So this would be A. And that distance right there would be B, down below. C is the distance from the center to each focus. There are 2 points in here that are called foci. And C would be that distance there. So with an ellipse, well, we don't need to go any further right now. We do have an equation here that describes the relationship of C, A, and B. Notice it looks a lot like the Pythagorean theorem, except for that minus sign. So watch for that. We always have to go back to this sheet to remember and get those right. With the hyperbola, we still have a squared, we still have b squared down below. Both equations equal 1, so that's not different. But notice we've got a minus sign here. Whereas with the ellipse, we had a plus sign. That's a huge difference. So if you have both x squared and y squared, with one of them being negative, you've got a hyperbola. Notice here we've got a y squared that's positive. Up above we have an x squared that's positive. And again, those are separated by this horizontal line. And so watch for that. If you have denominators that are different, but they're added together, you've got an ellipse. If you have denominators that are different, but they're subtracted, you've got a hyperbola. So there's a difference to watch for. Again, we've got a relationship of C, A, and B, though that one looks exactly like the Pythagorean theorem. Hyperbola, we already saw. We've got our coordinate system here. Hyperbola might look like a parabola opening up and down. We still have vertices here. So those are the vertices. We still have foci, but those are up here. The focus is always inside of the cup. We're going to see the same thing up here with parabola. We've got our coordinate system. If we've got a parabola here, the focus is always inside. The vertex is always that point of inflection. Now we've got this thing called a directrix. The directrix is a line that is equidistant from the vertex as the focus. And that distance is P. So that's the P that we're talking about right there in our equation. Every point on a parabola is equidistant from the focus as it is the directrix. So clearly I didn't draw this one quite right, but those are equidistant. So that defines the shape of a parabola, is that distance from the focus to the vertex and the vertex to the directrix. It will always be that way. So here's something to think about. This one that opens up or down, and we drew one that opens up, notice that the vertex and the focus are on the same vertical line. And that's why they share h. That doesn't change. P is the distance from the or the vertex to the focus, and so we're going to add p to the k value to get to the focus. Now, if this thing had opened left and right, let me draw one of those. We still have our vertex. The focus is still inside the cup. Notice those share a k value, but we're actually adding to the x value to get to the focus, and that's why here you add p to your h value. Another quick reminder is notice that with lots of these equations, every single one of them actually, we have a binomial squared. And the tool that we have used thus far in this class to get a binomial squared is completing the square. So you're going to have to complete the square quite a few times in this section. So that's kind of a quick overview of this conic summary sheet and a little bit about how to use it. We're going to go in and look at some of the work now and see if we can figure out how to use this with particular problems. But before I do that, I'd like to ask if you have any questions about this sheet, or even about the exams or signature assignment, anything like that. Just noticed we had a couple more people come in. Okay. All right. So let me open up the homework then, or the book, and pull out a problem and see if we can make this work. I want to get a good problem here. Okay, this one says, maybe I'll just copy it over from the book since I have the book open, and that way I don't have to write everything out. And you can read it better. Okay, they give us an equation and they ask us to find the focus, the vertex, and the directrix of the parabola. All right, so recall that, am I even sharing that yet? I don't even remember what I'm sharing right now on the screen. Okay, so let me grab my Conic summary sheet so that I can look at that without having to go back and forth on the screen. So for the parabola, here we've got x squared. And so I'm going to go to my sheet and I'll look at the top formula there that's listed as x minus h quantity squared equals 4p times y minus k. Well, I don't have anything subtracted. Well, I could rewrite this like this, negative 1/12 x minus 0 squared equals 4p. I'm going to leave that there for now, y minus 0. So we can see that h equals 0 and k equals 0. Just because our formula has nothing subtracted from h and nothing subtracted from x, I said h, nothing subtracted from y and nothing subtracted from x before it's squared. So let's see, I'm going to multiply, you know what, I shouldn't have written that 4p yet because I wanted the exact same formula. So there we go. I'm going to multiply both sides by negative 12 to clear that fraction out. So when I do that now, I've got x minus 0 squared equals negative 12 times y minus 0. So now it looks a lot more like our initial problem. And I've got this number here in the middle, this negative 12, and that has to equal the 4p. So over here on the side, I could just say, well, then negative 12 equals 4p. Divide both sides by 4, and p equals negative 3. Okay, so I've got h, I've got k, I've got the p-value. And so h is 0, k is 0. This will be the vertex of my parabola. If p is negative 3, and recall that the negative out in front gives us a reflection about the x-axis, so really I could say, well, negative means it's opening down, but regardless, I need to move 3 to get to the vertex, which would be right there. 3 the other direction gives me the directrix, so my directrix is right here. My parabola always opens away from the directrix because the focus always has to be inside the parabola. And now that I rewrote this equation into this form, I was able to find all that information. But to get other points on the parabola, I can just pick a point and plug it in. Say x is negative 2. So I can go to my function here, y equals negative 1/12 times negative 2 squared. So negative 1/12 times 4. So that would be negative 1/3. So at negative 2, it's negative 1/3, right about here. Positive 2 would give me the same thing. We understand the symmetry there. So maybe I'll try, I don't know, a number that would divide by 12. Just trying to simplify this. What if we tried x is 6? It won't be a perfect, yeah, it will. Negative 1/12 times 6 squared. Negative 1/12 times 36. So 36 divided by 12 is 3. So at 6, we've got a negative 3. Negative 6 would give us the same value. So there's the shape of our parabola. It's got this vertex, and it needs to hit those points. I didn't do a great job of it, but there's our parabola. They did ask us to graph it here at the end. But the focus is that point right there, 0, negative 3. The vertex is 0, 0. The directrix is a horizontal line at y equals 3. So now we've found everything that they asked us to find, and we went ahead and graphed this particular parabola. We used this formula from the formula sheet, and we converted the one they gave us into that format, and then we could read right off what is h, what is k, what is p, and that allowed us to graph this particular parabola. Again, really just using the information from our formula sheet. Another thing the formula sheet said was, I'll write it down here, The vertex is HK, which we got just fine. It tells me the focus is HK plus P. So that was 0 plus a -3, which gave us that one. We wrote that down here. They also told us that the directrix is y equals k minus p. And so that would be 0 minus a -3, or y equals 3, which we also got from our graph. So this information right here is on the formula sheet. I looked at the top half, or the top formula within the parabola section, and the focus and directrix on the top, because x was squared but y was not. Again, just pulling stuff right off the formula sheet to solve the problem they gave us. I think it's a little easier to solve it the way we did, by kind of graphing it as we went. But just plugging in the information we had seemed to work pretty well. Do you have any questions on this? All right, let me do another one. Slightly different in that they're giving us the vertex and the focus and asking us to find the equation. Grab another layer here. All right. So it says find an equation of the parabola with the vertex 0, 0 and a focus at 5, 0. So what I'm going to do is I'm going to graph those 2 points. There's my vertex. The focus is 5, 0. So I'll label that my focus. This one I'll call my vertex. The focus is always inside the cup of the parabola. So that tells me this parabola is going to open this way, so that the focus can be inside. Recall that the distance from the vertex to the focus is p, and that equals 5. I need to go the same distance the other direction to find my directrix. So the directrix is right there, and that would be x equals -5. There's my directrix. They gave me the vertex, and they gave me the focus. Graphically, I was able to determine p. This opens to the right, which tells me that y needs to be squared instead of x. So I'm going to write down the basic formula they gave me. Y minus k squared equals 4p times x minus h. Recall that the vertex is hk. So that tells me h is 0, k is 0. We know that p equals 5. So let's just plug all that in. Y minus 0 squared equals 4 times p times x minus 0. And now let's simplify this down. We've got y squared equals 20x. And there is the formula for the parabola that has the vertex and the focus that they gave us. And if they give you that information, go ahead and graph it to get a sense for what direction the parabola is going. It'll give you the p value right away. Then you know where on your formula sheet to look so that you can quick just grab the formula and plug the information in. That'll save you some time. Now, I did mention that we were going to be completing the square, and I definitely want to work through one of those problems before it gets too late to make sure that you see how I'm doing it so that you can do something similar. So let me grab a problem like that. So we've got this parabola. We're asked to find the vertex, the focus, and the directrix, and then draw the graph. They didn't have to tell me it's a parabola, though. In looking at this formula, I see that I have an x squared and a y first. I don't have a y squared. And so just seeing that, I know that this is a parabola because y is not squared, but x is. And since x is the one that's squared, I know this is opening up or down. I just know that because of the formula, and you know that. We've talked enough about parabolas that we can get this. So what I'm going to do is I'm going to isolate the y terms from, and the constant really, because I need to complete the square. So I'll keep this x squared plus 6x here. I'll leave some space and I'll move the y and the constant to the other side. And so now I need to complete the square, and if you'll recall, we take the middle term down, we divide it by 2, we square it, and add it back in. And anything I do to the left, I need to do to the right. So now I've got x squared plus 6x plus 9, which is a perfect square trinomial. That factors directly into the variable, and then the middle term divided by 2, quantity squared. Go ahead and add like terms over here. Now in our formula, the one where x is squared, I'm going to write that up here. We've got x minus h squared equals 4p times y minus k. So I've got my x minus h here. This on the right side looks a little odd. Maybe if I just factor out a -4. I'm going to rewrite this so it's x minus, and this has to be minus a -3 to give me the +3. If I factor out a -4, I end up with y minus 1. And now it is in the form of the equation on the formula sheet. So this tells me h is -3, k is -1. This is 4p. I need to solve 4p. I need to solve p. So I'll go ahead and set -4 equal 4p. Divide both sides by 4. And p is -1. So I could rewrite this as kind of a 4 times -1. So now I've got p there. So my hk is -3, 1. That's right here. There's my vertex. I should write these down. Vertex is hk, right off my formula sheet. So that is -3, 1. The focus, because the x term is squared, I'm looking above the dashed line. The focus is h k plus p. So I keep h. K is 1. I add p, which is -1 to that, and that's a 0. So -3, is my focus. The directrix, again, reading it right off my formula sheet, is y equals k minus p. So y equals, the k value is 1, minus -1 would be y equals 2. And that fits with what we expect. There's the y equals 2 line. It's on the other side of the vertex from the focus. So this thing opens down like this somehow. And the reality is I could set y equal to 0 and solve for x, and that would give me the x-intercepts. We've done that. You're familiar with that. But now we have the vertex right there. They want the focus right there. The directrix is always an equation, and we've got it graphed. Now again, in my math lab, they will want particular points. So what I will sometimes do is pick an x value and plug it in and see what the y is. Say an x value of 0. If I did that, those two terms would go to 0, and we would have -5/4, which is -1 1/4. It should have crossed the y-axis right here. So look for things like that that will, x values that will allow this to graph, because you'll be asked to graph it. And so I usually just pick an x value and plug it in and see what I get. Sometimes they will have you pick the graph from a set of 4 graphs, and generally speaking, they go different directions. So if you know this opens down, pick the one that opens down. If there are 2 of them, usually one is real skinny and the other's quite wide, and so pick the one that actually makes some sense. But that's how we would complete the square. A quick reminder of that so that you can get that done. Because we're going to be completing the square a fair bit. In 10.1, we're doing parabolas, just like we're talking about today. 10.2 are circles and ellipses, which are extremely similar to one another. 10.3 are hyperbolas. With 10.4, we're looking at inequalities. So at that point, you're looking at, oh, well, I'm shading this region, and how does that intersect with a line going through there where we're shading up above? Well, that's just this intersection. So that's what we're doing in 10.4, is something like that. But there's a parabola problem for you. I'd like to do another one. Let's see, let me copy it over. This one will be fairly similar to the last one, where we get to complete the square. Again, they didn't have to tell me it was a parabola. I've got 2 variables. One is squared, one is not. That alone tells me it's a parabola. But let's go ahead and isolate the squared term, similarities, and we'll move the x and constant to the other side. So I have y squared now. So my default formula where y is squared, pulling this from the conic summary sheet, looks like this. And again, the vertex is going to be hk. Because y is squared, I'm going to look at the information below the dashed line where it tells me the focus And when I say below the dashed line, I'm talking about the formula sheet, is H plus P, and we're keeping K. And the directrix is X equals H minus P. And you'll see that when we graph it out. So again, completing the squared, take that middle term divided by 2, square that result, and add it in. Anything I do to the left, I need to do to the right. Now I've got a perfect square trinomial, which will factor into the variable, and then the middle term divided by 2, and that will be squared. Combine some like terms. So I've got the left-hand side of the equation. The right side, I'd better factor out that coefficient to x. This coefficient now is going to equal 4p. Divide both sides by 4. And so I could rewrite this as y minus 1 squared equals 4 times 2 times x minus negative 4, just so that it's x minus like in our formula, and that tells me that I've got h, I've got k. Don't forget, h is always with the x, k is always with the y, and we've got p. And so now I can just write those down here. hk is negative 4, 1. And now the focus, I need to add p to h. P is 2. If I add that to negative 4, I get negative 2. I keep k. The directrix is x equals h minus p. H is negative 4 minus 2 is negative 6. And so now I can graph those. Negative 4, 1 is the vertex. Negative 2, 1 is the focus. I've got my vertex, I've got my focus. The directrix is x equals negative 6, which would be a vertical line through negative 6. And the focus is always inside the cup, so this thing's going to open to the right. So we found the vertex, the focus, and the directrix. We graphed it. That's solving the problem they asked. We had to complete the square. So you will need to remember how to do that. You'll have to use that several times. It works pretty well. Question I like to talk about now is why we care. What does the focus do for me? What does the directrix do for me? Why even solve for those? We seem to be doing fine before. Well, it turns out the focus is actually a very special point in a parabola. Anything that emanates from the focus or comes to the focus, when it hits the parabola, will be directed horizontally in this case. So if it hits the parabola, regardless of where it hits, it's going to fire straight out. And so I don't know how many of you have used a mag light, for example, one of those flashlights where you can rotate the head and it changes the shape of the beam. Well, when you get that nice narrow beam, what you've done is you've moved the bulb into the focus. And so while light is emanating in every direction from that focus, anything that hits the parabola of the shape of the head of the flashlight is going to be directed straight ahead. And so that really focuses your beam in and do a nice, small, round, bright light. as you move the bulb away from the focus, it will actually spread that light out because it will hit and bounce at an angle. To go the other direction, if we were, say, putting a satellite dish out, you might put the dish out and it may be only part of the focus or part of the parabola, just this small portion, but your receiver is at the focus. And so as the satellite imagery, the satellite signal comes in, it hits the parabola and is directed to the focus. So your receiver is actually picking up every signal that touches that satellite dish. So you're focusing all of that signal to one spot, which strengthens the information that you get on your TV and internet. I've seen people create a solar oven where they create a parabolic shape and cover it in foil or metal or something. And then all you have to do is put your food right here at the focus, and all the sun rays come in and they're directed directly at your food, regardless of where they hit the parabola, and it cooks your food. It does a really good job. So that's a real good reason to understand where the focus is, so that you can harness incoming signal, or you could emanate signal from the focus and send it to a very particular location. Those are good reasons we have to understand the focus. This question is same for a scope, and it would depend on the type of telescope. But yes, that is the same. If you can move the mirror so that it harnesses light and will send all of that minute bit of light from space to a central location, which is where your eye will actually be looking. Now you've collected a little bit of light and sent it all to one location, so that one location sees it as more light than it would if you just lit it with the naked eye. Maybe you've seen those solar collectors where they have a bunch of mirrors out there that gather and send that light to a central location where they actually melt salt, which has a lot of energy, and then as that melted salt hardened, it releases the energy and allows them to harness that. It's the same idea that you're talking about here with the telescope. We're collecting rays, sending them to one location so that it amplifies it. I think they've got some telescopic arrays that are created the same way. Allows them to collect a bit of light and magnify it and get a stronger image that we can review. Now, I can't give you a good reason to know the directrix, except for the point that every point on that parabola is equidistant from the focus as it is from the directrix. So the directrix allows you to create the parabola. But when it comes to world application, I really care more about the focus than I do the directrix. But those are good reasons to know those. Now it's just a matter of using this conic summary sheet and practicing how to use the formulas on there. We're actually out of time. I like this section, and so I guess I get talking a little bit more. Do you have any questions before we call it a day? Oh, my wife made some bread and I can smell it. She and my daughter have been in there working on that. It smells so good. All right, print out the conic summary sheet. It's in the course documents in the 143 Blackboard shell, and practice using that sooner rather than later. You want to be comfortable with that before you get to the test, so that the test is easier. Go ahead and start practicing your homework tonight. I think you'll be pleased with your understanding once you've got that sheet and start working through it. Have a good night, and I will see you tomorrow.
Thank you.
You're welcome.